Electricity is by its very nature an invisible force. To study it, harness it, or even track it flowing through a circuit, we first have to force it to interact with the physical world in a way our human senses can actually measure. The historical answer to this problem is the galvanometer. Looking at early models with their heavy brass housing and intricate analog dials, you can see it is a deeply physical, mechanical instrument. Its sole purpose is translation. When a faint electrical current, like the slight charge generated by a simple lemon battery, enters the device, the meter converts that invisible flow into a visible, physical deflection of a needle. Over time, this concept was refined into a highly specific internal architecture known as the moving coil galvanometer. Inside the casing, it operates as a carefully engineered arena where electromagnetic power and physical tension are pitted against each other to achieve a perfect, measurable balance. This diagram outlines the internal architecture of the moving coil meter. The environment relies on three core components: a multi-turn coil of wire wrapped around a cylindrical, soft iron core, sitting directly between two permanent magnetic poles. Notice the distinct concave shape of the north and south magnets. This geometry forces the magnetic field lines, mapped here by the green arrows, to point radially inward toward the exact center of the core. When current flows through the wire, the magnetic field exerts a pushing force, or torque, on the coil. We define this magnetic torque mathematically as the number of turns times current times area times magnetic field strength multiplied by the sine of theta, the angle between the coil and the field. Here is where the radial geometry solves a major engineering problem. Because the field lines point inward from every direction, the angle between the rotating coil's surface area and the magnetic field is constantly locked at exactly 90 degrees. The sine of 90 degrees is always precisely 1. Because of this, the sine term completely drops out of the equation, eliminating geometric variance as the coil spins. By neutralizing the angle, the engineering simplifies the physics. Any change in the magnetic torque twisting that coil is now strictly dependent on a change in the incoming electrical current. If magnetic torque were the only force applied, a continuous current would cause the coil to simply spin around forever like an electric motor. To function as a meter, it requires a physical limit. Looking back at the diagram, we find that limit located on the central axis, a small mechanical hairspring. As the electromagnetic force turns the coil, this spring physically twists. This creates a mechanical counterforce, a restoring torque, that fights back against the rotation. We define this mechanical resistance as K times phi. Phi represents the angular deflection, meaning how far the needle actually moves along the scale. The letter K is the torsional constant, which dictates the physical stiffness of that specific metal spring. This note establishes the critical state of the machine, equilibrium. The needle will stop moving across the dial at the exact moment the magnetic push equals the mechanical pull. By isolating the deflection variable, phi, we derive an equation that predicts exactly where the needle will land for any given current. The number of wire turns, the coil area, the magnetic field strength, and the spring stiffness are permanently built into the machine. Because those variables are locked in, the angle of the needle's deflection is perfectly linearly proportional to the incoming electrical current. Now that we can predict the needle's movement, we can mathematically evaluate the instrument's overall effectiveness. We define current sensitivity as the amount of physical needle deflection generated per single unit of electrical current. In parallel, voltage sensitivity measures how much that same needle deflects per single unit of voltage. Using Ohm's law, where voltage equals current times resistance, we can rewrite the formula. This substitution proves that voltage sensitivity is just the current sensitivity divided by R, the internal resistance of the galvanometer's own wiring. Because voltage and current sensitivity are mathematically chained together by the device's internal resistance, altering the physical design to improve one metric will inevitably impact the other. Let's test a hypothetical engineering fix. If we want to make the device more sensitive to faint currents, we might decide to pack far more turns of wire, increasing our N value, around the iron core. Mathematically, this looks like a clear win, because the number of turns sits in the numerator of our equation. Multiplying the wire layers absolutely increases the current sensitivity, but there is a hidden physical cost. More turns require a physically longer piece of wire, and longer wire inevitably creates proportionally more internal electrical resistance. This creates a design paradox. Because voltage sensitivity relies on dividing our result by that internal resistance, The initial gains we made in the coil are entirely canceled out by the resistance of the extra wire length. We can prove this limitation by running a mathematical edge case. Consider a scenario where modifying the meter successfully increases our current sensitivity by 20%, but the heavy modifications end up doubling the internal resistance. Setting up the calculation for the new voltage sensitivity, we substitute our new parameters, 1.2 times the old current sensitivity divided by 2 times the old resistance. Doing the math reveals a drastic reduction in effectiveness. The new voltage sensitivity is only 3/5 of the original value. Engineering the moving coil galvanometer is ultimately an exercise in physical compromise. Optimizing this instrument proves a strict rule of electromagnetism. You cannot cheat your materials. Maximizing one parameter inherently dictates sacrificing another.